Yes, so welcome everyone to this event. My name is Heidi Lagrasta. I am the Outreach Officer here at Max4, and it's our pleasure to be a part of Lund Sustainability Week and present this talk today about sustainability and research at Max4. I want to start off just letting you know that this event is live streamed and it will also be recorded. And we're hoping to use the recording in the future as part of our broader efforts to encourage researchers to join us in our search for the solutions to humanity's biggest and most pressing problems. So thank you for being part of today. I'm going to go a little bit over the schedule, but before I do, I want to say the event today is sponsored by Remade at RE. And Remade at RE is a EU circular economy initiative for the development of recyclable materials at Analytical Research Infrastructures, Analytical. And they coordinate access to 50 research infrastructures across the EU, including Max4. So we have an ambitious agenda today. I'm going to moderate, and I'm going to do my best to make sure we stay on time. I'll go through it briefly with you, just so you know what we're in for today. So first, we will have a presentation by Director Joachim Schnatt. Thank you. And we can show the, and then we will have a few presentations on sustainable research, starting with one on plasma catalysis from Johan Zetterberg and Sarah Blomberg from the physics department at LU. And then Nadia Day, who is Max4's European project coordinator, will give an overview of Remade at RE, along with postdoctorate fellow Santiago Pablo Fernandez Bordin. And then finally, Simon Escobar-Steinvall, who's a postdoctoral fellow at the Center for Analysis and Synthesis and a researcher at Nano Lund, will give a presentation on his research. It's a lot we're going to go through today, and I will ask you if we can do questions at the end, just so that we can make sure we get through all the presentations. You can then at the end ask questions from all of the presenters, and we'll even have 15 minutes afterward where you can go and chat with people outside the room if you have further questions. Yes. So, without further ado, I would like to welcome Joachim.
Right. So where do I click forward? Is that one?
Yeah.
All right, great. All right, I would like to say welcome as well to all of you. It's a pleasure to be here at the Pufendorf Institute together with you, talking about Max4 and sustainability. So I just try to move forward. Right. And of course, I should start by saying what Max4 is. Max4 is the National Swedish Synchronous Radiation Facility. And that, of course, puts the question right away, what's that? That's a difficult word to start with. Well, it's really the best light source for X-rays that we have in Sweden. And actually, it's one of the best sources for X-rays in the world. So if you think of visible light, and of high quality light, then you typically think lasers. Now, Max4 is not a laser. It's a synchronous light source, but in a way, it's parallel to lasers. It is a facility for producing very high quality X-rays, much better than the quality that you normally would get at the hospital or what you would get at the airport and so on. I'm not going into what this means because there's a couple of different things that is coupled to the quality of X-rays, but just think of it as one of the best sources in the world for X-rays. That we then can use in order to study a whole range of different things. And if I say we, it's actually not us at Max4, is our users. Max4 is a user facility. That means users come to us from all over the world and do experiments, and they study, for example, materials, health materials, questions from the environment, and all goes back in a way to the atomic level. And hopefully we can then use that information that we get, our users, the researchers, to answer fundamental questions, both as well as applied questions. Sustainability is really an extremely important thing in many of the research endeavors that are being carried out at Max 4. Just a word on where our users come from. More than 40% come from Sweden, mostly from universities, but also from industry, for example, and other institutes. Another more than 20% come from the other Nordic countries, and the rest comes from all around the world. Actually, last year we had users from all continents but Antarctica, so that was quite successful. And you see that we have on the order of 2,000 users that come to us each year. The most important thing that Max 4 can do for sustainability is research and supporting the researchers that do sustainability research. And I just would like to give you a very quick flavor. We're going to have a bit more extensive versions of research examples that was automatic a bit later on. But just to give you a flavor of the things that you, for example, could think of. One of these is examples that are shown here, which is about circular and sustainable materials. And this is a study that Tetra Pak, or that's lying behind what you see here. So Tetra Pak came to Max 4 in order to investigate paper straws. And you all know about the EU regulations that plastic straws are not allowed anymore and that they have to be replaced by other sustainable materials. And Tetra Pak studied the materials behind these paper straws. And what they said is, without the results at Max 4, we wouldn't have been able to have a product now. That was an extremely fast development, just took sort of like half a year. And from the idea and the material up to the product. And that was an immense success for Tetra Pak, and you can imagine how important that is for both the company, but also for their sustainability program. Another thing that is, of course, very prominent when you talk about sustainability is energy and energy production, energy storage. And here is an example of research on energy storage. So that's on batteries. And with batteries, you have always the question how to charge them in a way so that they actually give the best output at the same time they actually have a high lifetime. And that is not so easy to answer because there's a lot of chemical processes going on in these batteries. And if that was running, but unfortunately it's not running, you would see actually that things are changing here in this view graph, which is a structural characterization of the batteries while they're being charged. And this is something that really not can done in very many places, just looking at what is happening exactly in these batteries. And the answer is, it's given here in the middle, is that, well, what is seen here from that research is that the material doesn't charge homogeneously, and that is a problem. But by looking at different parameters, for example, you can optimize these battery materials and in the end get better batteries that hold for a longer time and do a better job. And of course, that is extremely important for sustainability. I know it's working. I'm sorry. I should have clicked another one. I go on anyway, just to give a very a last very short brief example here, which is on algae for water treatment. Water treatment, we talk about algae blooming in the Baltic Sea, for example. You all know that this is a huge problem. And this, what is behind is that there's a lot of phosphorus coming into the water. So the phosphorus has to be removed from the water, wastewater. That can be in different ways. And one way of doing that one is to use algae actually to, so to say, eat the phosphorus. But how exactly this works is not being known. And here you actually see algae cells where we studied where the phosphorus actually accumulates in these cells. And you see, well, the red points up there in these view graphs, that is where there's a lot of phosphorus, and that is then quantified down here. Where it's green, it's less phosphorus. But what we actually see from that view graph here in C is that, well, the amount is not so very different. This is one information that we get out here. The other information that we get out from this view graph C is actually that the chemical state of the phosphorus is the same and of a certain class all over the cell. So it's more accumulated at some places and less accumulated at other places, but the chemical state is everywhere the same, which means here we get very important information about the chemistry that is going on in these algae. Right. Sustainability, there are tons of projects, of research projects being carried out at Max 4 on sustainability. You see a list here. I've been mentioning a couple of areas, but it could be whatever. Sustainability is, of course, not only about the research, but this is the best thing that we can do for favoring sustainability, but it's also at the heart of what we do. Otherwise, we are very aware about the carbon footprint that we have. For example, we do have a very high energy consumption. It's on the order of 1,400 buildings for living that we consume each year. This is actually much less than what you see at other facilities because we have such a good scheme for producing the X-rays. But of course, as we know from the sustainability goals of the United Nations, also things such sustainable workplace and financial sustainability are very important when you talk about sustainability. Right, the building is built in a very good way for sustainability. I've been bit in here. I just want to point at this number here. The clever building design cuts the energy used by 30 to 50%, and that means the building design is also the accelerator. It's much less than what you would have at a comparable facility anywhere else in the world. That's actually quite fascinating. And we do return heat to Lund. So something like 1,000 households. I've been mentioning industry, Tetra Pak. There are many other industries coming. I can't mention all of them because it's proprietary research, but there's a lot of sustainable research going on at these industries as well. And this is partly in collaboration with the academic users, partly it is being sold to these industries. Right. I do think that we will see an increased focus on green innovation in the future in what is being done at Max 4. We just could read in the newspaper that sustainability is climbing up in the agenda again. Very luckily, I have to say, that we can think of it again. It is an extremely important question for our future. And of course, we also will do our best in order to make the work that we do at Max 4 directly sustainable as well. This is not always easy, I should say, but we do have a plan and we'll work on that. And I think that needs to be enough. I've already gone over by 2 minutes, so I leave over to next to present us. We'll do that together, I think.
Thank you, Akim. And I should say that the program said that Akim is our interim science director, but he is in fact our permanent science director now, and we are very glad. So, okay, from 1st of July, and we're glad to have him. Yes, so Johan and Sarah, would you like to present your research on sustainability?
Yes, thank you. And it's great to be here. I'm glad to be here. Thank us for having us. So we're going to talk about plasma catalysis, a sustainable way forward. And the reason why there is two of us, because the area of plasma catalysis is extremely complex. And in order then to understand this, we need several different areas. We need to understand catalysis, we need to understand surface science, we need to understand plasma, and we need to have the different tools to understand it. That's why there are two of us today. We're 3 PIs that are driving the project, me, Sarah, and Andreas, who's not here today. But let us kick off with the global energy need that we have today. And if we look at this, we can see that the energy need continues to increase. And this is over the last 30 years. And the good news is that our oil dependence is down by about 7%. But the bad news is that we use about 39% more oil now than we did 30 years ago. So it's here. It's going to be difficult to get out of it. And if we look at it, we have oil, coal, natural gas, biofuel, and waste, and all that stands for about 90% of our energy production. It's all combustion. So there has to be ways forward. What could it be? Is catalysis one of them? Well, first of all, what is catalysis? It was a word that was coined by the Swedish chemist Jöns Jacob Berzelius in the early 1800s, and it's a substance that can change or modify a reaction rate of a chemical reaction without actually being consumed itself. That means that it lowers the amount of energy that you need in order to have a reaction going. But it's also selective, so it can choose which path this chemistry is taking. Right? And it's all over. It's in power plants, it's in industries, it's in cars, you see it everywhere. And one very important place where you see catalysis is in the production of ammonia. And ammonia, from ammonia, we produce synthetic fertilizers. And synthetic fertilizers today feeds about half of the world's population. So you can see when we started to produce synthetic fertilizers on a larger scale around the 50s, well, you can see that the world population just skyrocketed. And it's because we can produce much more food, right? So ammonia production is done via the Haber-Bosch process, and it was brought forward by the two Germans, Fritz Haber and Karl Bosch. And in the beginning of the last century, you basically take nitrogen, you take hydrogen, and you produce ammonia from it. And it's a process that's virtually been unchanged over the last 100 years. It's energy demanding, so even though you have the catalyst, you can bring down the temperature quite severely, it's quite much, but you still need high temperatures, about 500 degrees, between 200 and 300 bar. This is a lot of energy, and all of that energy more or less comes from fossil fuels. That means that it stands for about 2% of the global energy consumption. That's quite a lot, right? And about 1.5% of the CO2 emissions in the world. And another reason for that is that all of the hydrogen, more or less, that you're using to produce it is from natural gas. So it's all fossil. So there has to be a way forward. Can there be a way forward without sacrificing half of the world's population? Well, let's hope so. Catalysis is good, and it's used today, but it's probably not enough to solve our problem. But what if we can use the benefits of catalysis? What if we can use this energy-saving thing that you have and the selectivity that you have so that you can steer to know what products you're getting? What if you can manipulate the surrounding that you have around your catalyst without elevating the temperature and pressure using fossil fuels? What if you can use something like plasma instead? And plasma is used in a lot of different applications. You can use plasma to transfer electric energy then to gases and liquids. And it's done in thermal applications, for instance, methane cracking. You can use it for sterilization and etching in non-thermal applications. And you can mix them, for instance, in plasma reforming. But then let's have a quick look at what plasma actually is. It's the fourth state of matter. It's very energetic. So it consists basically of free electrons and ions. And there are also excited species and radicals. So it's extremely reactive, an extremely reactive environment that we have. And here's an example of an arc. So this is a gliding arc. You have basically just a discharge between two electrodes, but as you can see, around that sort of greenish discharge, there is a glow to it, almost like a campfire glow. And this is taken in just an atmosphere of nitrogen and methane. So what's happening is that we're decomposing methane to carbon and hydrogen. Right. So obviously, it's a very reactive environment, and there are some things about temperature that we will talk about soon, but it's really difficult to understand. So the thing is, how can we understand it, and how can we control or steer it? Right. So let's just quickly go through that there are two different kinds of temperatures that are involved here. You have something that we call electron temperatures, and that's how fast the electrons are moving, and then we have the gas or ions and neutrals temperature, which is the temperature we usually think about. That's what we measure with a regular thermometer. It has to do with the velocity or the speed of our molecules, right? So in thermal plasma, the electron temperature and the ion temperature is the same. You know, it ranges from several thousands to tens of thousands of degrees. So it's really, really warm. And then you have non-thermal plasma, where the electron temperature is really high, but your gas temperature is low. So that's what you can put your finger there. It doesn't really hurt. And then, of course, there are all these intermediate things. So what if you can use non-thermal plasma, where you put less energy into it, and still have a very reactive environment? So how do we study this? Well, we study it with lasers usually. And from that, you can get temperatures, because you can't have a thermocouple or something like that into your plasma. It'll burn. There will be nothing left. So you have to look at the light. Right? So you send light in, you take light out, and then you can measure the temperature. You can measure different time scales, because you're Lasers can be pulsed. You can go down to picosecond level to really understand the dynamics between the electrons and the particles. You can follow very complex chemistry because we can follow this in both time and spatially. So we can study the high energetic electrons, and we can do that simultaneously as we study charged particles and radicals that are only short-lived and there for a very short amount of time. We can't do this with anything else. We can get high spatial resolution. It's more or less unintrusive. If we shine the light in, we just look at the light that is coming out. And this is just an example where you have a discharge, and the blue thing there is fluorescence from OH, in this case, a radical that you can see then and see where it is and how it interacts. And we can do this in situ, but to know a little bit more about in situ, I think it's better that I turn over to Sarah.
Thank you. Yes, so Johan talked about lasers, and you know, Lund is very known for lasers as well. The Nobel Prize in Physics was actually based on laser measurements. However, as Akim just said, we have also the best synchrotron in the world over here. And of course, we want to use that. And I do that to study materials. And as Akim also said, the synchrotron produce X-rays. And we use X-rays to study material and material properties, so solid materials. There was actually also a Nobel Prize in the beginning of 1900. A lot has happened since then. So when you go to Max 4, you have different beam lines. And that means that you have different experimental setups that you can use. So you have to choose which of this setup you want to use and to study your material. And in our case, it's the catalyst and the catalysis processes. And what can it actually look like then? So this is Max 4 is actually 2 synchrotrons, what you can see here. What can it look like? Yeah, this is 2 photos from 2 experimental setups. As you can see, it's a lot of equipment, a lot of stuff is going on in there. You hardly never see your sample. When you put them in, and then it's a lot of different experimental setups around it, and you hardly see, as I said, the samples again before you take it out, of course. The technique we are using is also based on a Nobel Prize from Albert Einstein, the photoelectric effect. And this photoelectric effect was discovered by Albert Einstein, but it was also developed by Kai Siegban, and to a technique that we can use. Kai Siegban was actually working here in Lund, but then moved to Uppsala and got the Nobel Prize for this technique. Just wanted to mention that he started here. However, it's 2 beam lines that we have been using. It's called Hippie and Species, and the technique that I just told you about is called X-ray photoelectron spectroscopy, and it's called XPS. In this case, as I said, the X-rays are used from the synchrotron, or knock out one of the electron, which is the photo electron, and we can measure the energy of this electron. And that carries a lot of information to us about the material that it comes from. So, for instance, it's species specific, so we know exactly what kind of element we are probing. And it's also chemical sensitive. So depending on the chemical surrounding of this atom, we know we can get a lot of information about the structure and how these atoms are arranged in the material. And for instance, we can also see, so for instance, if carbon is binding to another carbon, we can measure that at specific binding energy, as we call it. But if carbon binds to an oxygen atom, it will show up as at a different energy. And by that, we can get this kind of information. And that is very useful for catalysis, because then we have the interaction between gases and material, or in this case, plasma and the material. At the beamlines, well, we, as I said, mainly see screens and computers. So here you can see just an example. It's very modern, and you don't do much by hand. Most of the things, you press buttons, and you have to know which button to press. And you get out different kind of spectra in this case. This is actually the catalyst, what it can look like when we put them into the setup. It's an industrial catalyst that we use. As you can see, it's solid material. It's sort of powder. But what we get out is not an image of the catalyst. So what we get out is something that looks like this. But that carries both chemical information and structural information. So it's sort of a fingerprint that we can use and know exactly what the material looked like. And then we can, for instance, so here it's a ball model, so the balls are atoms, and it's the blue and the red are different kind of atoms. But we can get this kind of very detailed information, how the structure looked like on the catalyst on an atomistic level. And now comes into this in situ experiment, as Johan talked about. Usually when you perform experiments in your home lab, what you do is you have your catalyst, you expose it to different gases, and then look afterwards what it looks like, because you don't really have the tools to look in situ. But we would like to look into this process while it's actually happened, while the catalyst is active, while the interaction is going on. And that you can do at Max 4. Why do you want to do this? Yeah, well, this is an example. It's a sketch. So this, for instance, is before and after. As you can see, it's not much different between these. But then it's a lot of things that's going on that we don't see if we measure before and after. We want to see what's going on while the catalyst is active, while all these things are happening. Then we can get detailed information about the reaction and how it actually occurs, like this. Here we know exactly which atom are interacting with the gases or the plasma. And then we can get a better understanding how the process actually occurs. However, plasma catalysis is really challenging. It's really challenging to study both plasma and also to do this in situ experiments. We don't have much time. When you go to Max 4, you maybe have 5 days. And in that 5 days, everything has to be perfect. Otherwise, you don't get out there with the good results you want. So we did the first plasma catalysis experiment at Max 4, and it's actually the first experiment ever performed at the synchrotron. So we come up with this idea, and this is the chamber where we put in our catalyst. And as you can see, it's slightly light blue in the window there, and that's because it's plasma in there. And also we have our catalyst in there. The catalyst looks like this. In this case, we had a gold and a nickel catalyst that we tried. Inside the chamber, it's a little bit hard to see, but it looks like this. So here is the plasma and the sample is in there. This is a more close-up to the sample, what it looks like. The cone is where we collect all the electrons. That, as I said, is the fingerprint of the catalyst. And also, we get very close to the catalyst, where it's directed in this. Yeah. And then what we measure, as I said, is spectra. And we have to interpret these spectra, and that's what we do maybe several months after we get back from Max 4. And we have to try to understand, what does this spectra mean? In this case, from this spectra, it's hard to say for you, I guess, but I can tell you what we could see is that the nitrogen, where we have a plasma atmosphere of nitrogen and hydrogen, so for the ammonia production, we can see that this is nitrogen adsorb and then dissociate, which means that it's actually nitrogen atoms on the catalyst. And that is exactly the first step of the catalysis process of ammonia. So we can see here the first step in the ammonia production using plasma catalysis. So this is done at atmospheric, it's actually below atmospheric pressure, but at room temperature. So not much energy has to be done to see this kind of effect. So, from a first step, it works, and we can try to get very fundamental understanding on this process. And hopefully we have an upcoming beam time that will do more of these and see if we can understand more of these processes. And hopefully also then provide industry with information about this so we can actually put it into more industrial processes and then produce ammonia in a more sustainable way. So in summary, yeah, as you know, we consume too much energy, and it's mainly based on fossil-based feedstocks, and we have to go away from that. And production of ammonia is one of the worst, but we need ammonia. So plasma might be a way of using and to activate the reactants in another way than temperature and pressure. And then we can use also catalysts to steer the reaction. But it's really challenging to understand. But we then think that MAX 4, then we can study the process and the catalysis process. We have the tools from the laser diagnostic to understand the plasma. And we can combine this, and by that get a unique opportunity to study plasma catalysis and understand that in a more better way. So the people that is involved in this project is mainly from the Division of Combustion Physics at the Department of Physics, and it's also Department of Process and Life Science Engineering. We have the people from MAX 4 that have been helping out, and a lot of foundations that have given us money to do this kind of research. So we would like to thank them, but also you for your attention. Thank you.
Thank you so much. That was wonderful. So great to hear about what you're doing at MAX 4, and I look forward to learning more in the future about it. So now we're going to shift from some experiments that happen at MAX 4 to looking more at Remade, at ARI, and all of the things that are happening on an EU level connected to the circular economy. So I'd like to welcome our next guests to talk about that.
Thank you very much, Heidi. Good morning. It's great to see so many people here in the room interested in this subject. My name's Nadia. I'm here as project coordinator for Remade at RE, which is a project that spans about 17 different countries across Europe and over 50 research infrastructures. We only have 5 minutes, so myself and my colleague Santiago will just give you a very brief overview of what the project is and what we do. We are a hub for material research, so we are looking at recyclable materials development at Analytical Research Infrastructures. MAX 4 is obviously one of those research infrastructures and is involved in the project, but it's one of many infrastructures that is part of this project. Who are we? We are a consortium of over 50 partners providing free access to the research infrastructures. And by free access, we mean the actual access to the research infrastructure itself and also financial support to the researchers that come to see us. We are a 4-year project, so we started in 2022 and we will be finishing in September next year. We are funded by the European Commission. The majority of our funding comes from them, 13.7 million, but also we have 1.8 million from the UK and from Switzerland. And because we have so many research infrastructures, we have access to a very wide network of experts in various fields. So we have over 150 researchers and instrumentation scientists who are involved in this project. And we also have 20 junior scientists or postdocs, Santiago being one of them, based at these different research infrastructures who support our researchers wherever they might be going and whatever they might be doing. So we are a very large team dedicated to promoting materials research. We are involved in both the academic side and in the industry side as well. And we are really here to support researchers looking for solutions to moving towards a more circular economy. So what do we offer? Across all of our research infrastructures, we are offering over 50,000 hours of transnational access. So what does that mean? Transnational means that if you are based, for example, here in Sweden at Lund University, you are welcome to come to MAX 4 and Lund University and everything that it offers. But in terms of our project, we will support you to go to a research infrastructure in a different country in Europe. So we will provide that free beam time and we will provide the financial support to access that facility. We provide many complementary techniques. I manage the online platform myself, so you're very welcome to go and find us on the online platform, visit our website, and Santiago will give a little bit more information about the different types of techniques that we have. As I say, we're open to academic and industry. and you can visit our webpage to see when our portal is open for access. And you can apply in any of these areas, for example, batteries and vehicles, food, water and nutrients, textiles, and as Achim mentioned, batteries are very high on the agenda at the moment. These are all areas that are supported by the European Green Deal, which is part of the Circular Economy Action Plan. So you're welcome to find more about that online. I'm not going to go into detail about that today. But we support all of these areas across Remade at RE. We have outreach and training to new communities. So we're not just about experienced researchers coming and doing research, but we support inexperienced or lesser experienced researchers to come. And also, of course, with the transnational access, as a researcher, you have access to facilities that maybe you wouldn't normally have as part of your country. So from that, I will pass over to Santiago to say a couple of words about the techniques.
Thank you, Nadia. So through Remake project, you can access a different technique. It's a large amount of technique with different sources. You can have an experiment with neutron, X-ray, positron, electron microscopy, among others. And the good thing is that you don't need to be expert to have access to this technique, because you can have support through the Smart Science cluster. The idea to have support is starting sending a pre-proposal that only you answer some question about what is your project, what are you interested in, measure. And then one of the junior scientists will contact you, and then we will have a discussion about your experiment. I will recommend you some techniques that fit with your experiment, and then how you can perform your experiment. And then you can send the final proposal that will be evaluated with the committee. Once your proposal is approved, also we can support your experiment in situ and ex situ. It's like if you need support doing the experiment, we can travel with you to the facility and support you during the experiment. And then the good thing that also you will get support with the data analysis. So you can be like a beginner or no user with the technique. You can have like a really nice result. This is the Smart Scientist. We are located at different facilities. We have different background with different expertise in even with technique, also with the sample materials. So it's a really nice opportunity if you have an idea or you are interested to have like a new experiment that you are not related with. You can apply. You will have support during all the process to get very nice paper at the end. So Nadia, if you want to continue.
Yeah, just to highlight that we have a lot of information online as well. We have webinars online, and the information today will be online as well. So we really try to make the education and training a large part of our project. So these are the webinars that we had in 2024. We have them also going on in 2025. So you're welcome to check out our website and find more detailed information on those there. We're a very large team, and we are really trying hard to push this project towards research more towards the circular economy. So we really welcome your questions and interest after the presentation. Thank you very much.
Thank you. And finally today we have Simon Escobar Steinvall, and he will be talking about his research with solar cell material and nanoscience.
So, thank you. As soon as there we go. So, yeah, thank you for having me here today. So, yeah, so what I'll be talking about today is more what I, as a user of the different facilities, do and why I will need this type of, well, support in advancing my research. So, to start off, what is a solar cell? How does it work? So, we have often a semiconductor in the solar cell where we'll have two energy levels. We have a so-called valence band and a conduction band. And when the light shines in, it will be absorbed and will excite an electron from the valence band to the conduction band. And that's the first part of a solar cell. It has to be able to absorb the light, and then we want to make it, well, produce electricity. We want to be able to actually use this in our everyday societies. Then we want to separate the electron and the so-called hole, the absence of the electron, and be able to extract this in order to use it. So today, most solar cells are made from silicon, which due to the electronics industry, we know how to do the charge separation and extraction very, very well. However, it's actually a lousy material when it comes to light absorption. We need very thick layers, and it limits how we can actually use it. Any lightweight or flexible applications we can't actually do. If we want materials that can do both of these today, we need often very expensive materials such as gallium arsenide, or we need something that's unfortunately toxic, such as cadmium telluride. Now, a lot of research today is to look at more, well, safe and sustainable materials that can potentially do both of these. And that's kind of where my research comes in. I look at a material called zinc phosphide mainly. Now, this material is extremely good at absorbing the light. However, the charge separation and extraction has been a challenge for many years. So that's when the second part of the title comes in, nano. So here in Lund, we have Nano Lund, which I'm part of. And I'm trying to use different nanoscale techniques, which I'll explain in a little bit, such as nanoscale epitaxy, to improve the material quality and how we integrate it with other materials in order to help it with the charge separation and extraction. So when you combine materials, there's a technique called epitaxy, which comes from the Greek, which is essentially how you would deposit a crystal on top of another. So we have the blue material, which is the material we're trying to grow, on top of the red material. And if these are two good crystals, the blue material will adapt the same structure of the one below. So if we see each dot here as an atom, then you see that the blue layer conforms to the bottom layer. However, this only works if the atomic arrangement is very similar. If you have a very different atomic arrangement, you'll start to introduce so-called defects. So misfit dislocations and other type of defects, as we see there on the right. Now, one way to avoid this is to make the interface areas very small. So we want to make them nano-sized, because then there are different ways to actually avoid the formation of these defects. Because these defects would make the charges go back, and we can't extract them if we have them in the material. So first way to do it is to look at, well, so-called vapor liquid solid growth. So what I would do is I have a substrate, so a surface where I then come with a gas and I deposit this particle, which will be a nanoparticle in the order of 10 to 100 nanometers, and it will be liquid. And then I supply more gases, so I would supply zinc and phosphorus in gas form to this liquid nanoparticle. And when this one becomes full of zinc and phosphorus, it will precipitate out some zinc phosphide. Now, it would preferentially do it at the interface with the underlying substrate. So that is where it will be easiest. And if it does so again and again and again, it will grow into this nanowire, because it will want to grow in the same direction and deposit the material at the same place every time. So that's how I would grow a nanowire, using this catalyst particles. Then we have the vapor phase, which is the gas. We have the liquid, which is the particle, and the solid, which is our nanowire. Another way to do it, which actually will be the main focus of this talk, is so-called selective area epitaxy. So then I have the substrate where I grow on, and I have a small mask layer on top where I make nanoholes. And in these nanoholes, I can make the material selectively grow inside there. So then I can also limit the area between the material I grow and the substrate to help reduce defect formation. Now, again, I supply the gases that can go around the surface, and it can also lead to a nanowire grow. But the question mark there is because I tried this in my PhD to grow nanowires, and I failed spectacularly. That has led to me, well, to my last 5 years of research. But I'll get into that as well. So, how do I apply this to zinc phosphide? So, nanowires grew very nicely. I'll very briefly touch on that. But the selective area epitaxy, as you see there, it's not nanowires. And we'll talk about that more in detail. And while I focus on zinc phosphide here in Lund, we're also collaborating with other, through this EU project called SolarUp. We're also working with other people in Sweden, such as in Uppsala and at Kyoto University in Japan, to try these approaches for other materials as well for solar cell applications. Now, I'll very quickly go on to this nanowire bit, but because it's not too relevant to the remade at RE. But yeah, what I did together with a recent master student was that we were trying to eliminate all the scarce element in the process, because even though zinc phosphide is earth abundant and good for sustainability and so on, it used a lot of indium in the process of making this material. So together with Hampus, my master student, we replaced indium with tin as the small liquid particle, and on the substrate that we grew, we started using silicon. And we thought, great, this is going to be a very straightforward process. But we started getting triangular, pentagonal, and these zigzag hexagonal nanowires. So in terms of crystallography, having pentagonal crystals is something that's very strange. We've managed to explain it. It's not something like quasicrystals or anything fancy like that, but I don't have the time to go into it today. But this was a very interesting project, and we're starting to push this towards more sustainable materials. So the next step is actually using these in solar cells. But I'm going to go back to the selective area epitaxy. So the way this works with zinc phosphide is we have this hole where we're trying to grow selectively in. We deposit zinc and phosphorus, and it starts to grow in the hole. And then when we thought we were going to start growing a nanowire, it started growing like a pyramid. And with enough time, it grows into a full pyramid. And if you have them next to each other, you get these films with a pyramidal texture. Now, if you look at a silicon solar cell with the highest efficiency, they actually try to achieve this texture by introducing extra etching and processing steps. So they do extra work to try and get this texture that we're getting for free. So I was trying to grow nanowires, but I got this instead. And now we're 7 universities all across Europe trying to develop this further through this EU project. Now, when I did this initially back in Switzerland, where I did my PhD, we were using so-called molecular beam epitaxy to grow the material, and we were using electron beam lithography to make these small holes. Now, these are very good techniques for looking at the fundamental of crystal growth and making materials, but they're not very scalable. So if we actually want to see any impact of our research, we had to go to other techniques. So when I came here to Lund back in the end of 2020, what we've been looking at is using techniques that we specialize in here that are more scalable. So metal organic chemical vapor deposition is something that's used in industry to grow, laser materials, for example. And we have a very special technique here in Lund called Talbot displacement lithography. Now, I'm not really going to go into much detail of it, but what we use is ultraviolet light and use the interference of photons to make very small holes in a periodic pattern over large areas. So for what we want to do in solar cells, this is perfect. So combining these, this is kind of how these arrays of pyramids look on a substrate. So this was looking very promising, and together with my PhD student Aides, we have then developed them into growing these thin films here over large areas. So it's all going in the right direction. But in order to understand this, we have to ask, do we still have any defects? What type of defects do we have? And how do they affect the material? And that's when we turn to remade at RE, because then we can use these state-of-the-art facilities. So as we're here in Lund, we can't use Max 4 through this. We have to go somewhere else. So we went to the Alba synchrotron in Spain, where we could carry out these experiments. We actually, I say we, but my PhD students, and he got some support. They went at the beginning of last month, in beginning of April, to go and do these experiments there at the Alba synchrotron to try and understand the defect formation in the material, see if there's something how it impacts the material, and so on. And that's, as was mentioned in the earlier talk as well, they were there for 4 days intensively doing experiments, and he's probably going to be analyzing them for the next few months. So, to summarize, using the techniques that I have been developing for the last few years, we've developed, well, some high-quality zinc phosphide in form of nanostructures, and the properties seem ideal for solar cells. So actually, we've broken some records when it comes to this type of material very recently, and we're now starting to achieve it using more scalable and industrially friendly techniques. So now, yeah, we're starting to use it in more devices. We want to perform more characterization and explore how this technique also can impact other materials. So, as always, I am here presenting, but science is a group effort. I want to especially thank the students who've been involved in this, the other people in the group, the collaborators at the Alba Synchrotron and ICN2 who were part of this remade project. And yeah, I guess, well, there will be time for questions after all of this. Thank you very much.
Thank you so much. I think all of what we've heard here today really underscores the fact that materials research is at the heart of sustainability, and finding new ways to use materials and creating new materials and new structures, it will lead to solutions to a lot of our problems with energy and other fields as well. You did so well keeping to time. Thank you. I know I've pushed you along, but we do have a few minutes now for questions. So if anybody had a question for one of our panelists, I have one if nobody does, but Nadia, maybe you can take a microphone around if we have a question from the audience on any of the presentations that we had today. Yeah, would you like to stand so they can point at you and pick a person? Well, I think I'll start off with one then, as I had a question for the panel, which is, and maybe this is for Akim most of all, where do you think researchers should be focusing in order to make the greatest impact in terms of solving issues related to sustainability? And what are the barriers to that?
Well, this was an extremely wide question.
Yes.
And there are tons of different researchers. So you say perhaps you should focus a bit on the researchers that we have at Max 4 or other facilities such as at Alba, which is the same kind of facility as Max 4. Where should they focus? I think we've seen quite a lot of what the focus is today, and that's probably the focus that we need to have also in the future, and you also said it. We're not going to solve our problems without materials, and this is where we really can make an impact. So I think focusing on the properties of materials, thinking about how to produce materials in a green way. There is the topic of green chemistry. For example, that means using less raw material, using lower temperatures. We were talking about plasma catalysis here, putting in less energy and so on. This is an extremely important topic, so that we can get rid of the waste and that we can produce really materials in a direct way. This, for example, is an extremely important question. All these questions of energy is an extremely important thing for sustainability. We're not going to do without energy. Of course, it's a question that we then perhaps should use less energy than we're doing today. But whatever we're going to do, we're not going to do without energy. So energy materials are, of course, extremely important for sustainability, and that we have to develop better materials and better processes as well for these materials. Then you could wind into so many different areas as well. One of the things that we haven't been talking about at all here today is life science. But life science has a lot to do with sustainability as well, because that is, so to say, also if you look at the sustainability goals of the United Nations, life science health is an extremely important topic, and that we also can make a real difference. And that is something that we're just realizing, the potential that facilities such as Max 4 and other facilities actually have. I think I can't answer your question. It's too wide.
Well, did anybody else want to weigh in or say anything related? No? Okay. Do we have any? Yeah, one over here, and then we'll take one there.
Is it on? I think it's on. Try.
Yeah.
No?
Okay. Yes? I think it's okay. I can also. So I have a question to the plasma group actually. So you didn't mention the example, but I mean also transportation of green hydrogen may be benefiting from this approach that you're trying. Yes. So that you just mentioned the pathway from hydrogen and nitrogen to ammonia, but the other way around should be actually working as well, I suppose, in some conditions, huh?
Absolutely. I mean, ammonia is. I mean, if you ask Siemens, for instance, who build gas turbines, they see ammonia as a nitrogen carrier, and that's it. So ammonia is a very good hydrogen carrier, and can be used as a fuel. But it can also be used in fuel cells, for instance, and so on. So, absolutely, that's one of the solutions. I think having huge tanks of just pure hydrogen is going to be very difficult. That infrastructure is going to be very difficult. So ammonia is a solution there, yeah, absolutely.
Great. And I think we had one over on the other side. Nadia, if you can.
I want to ask the plasma group too. You talked about this, the energy it takes to create ammonia today. But how much energy does it take to create your way? I know it's still experimental, but any idea about it?
Would you like to answer that?
I feel that's a main question, really.
It's a very difficult question to answer. I mean, we don't know yet. We have no idea. Okay. And the reason for that is that we don't know the pathways yet. We know that we can split nitrogen. That's where we are. But then we have to form ammonia afterwards and get the nitrogen to actually leave the surface, and so on. So there are more steps here. So plasma in general is being used and is being pursued at the moment for a lot of different, as I mentioned, reforming and so on, for the reason that we believe that we will be able to use less energy than with thermal processes. We're not there yet in every way, but we are there in some processes, and I think that it's an avenue that we have to take. We have to take every avenue that we have right now, because we have to make it work on many different fronts in order to bring the energy consumption down. And I think low temperature plasmas, but sometimes also thermal plasmas can be a way of moving forward. Absolutely.
Okay.
Great. Any last question? No? Well, then I will say thank you to the audience for your good questions and to our audience online. And we will, if you have other questions for them you want to take in the lobby, we'll be outside for a few minutes. And thank you to Lund University for this opportunity to present our research today. So thank you.